Last time we were working on some homework problems, so we want to continue working on those today. There were some requested problems from the chapter 5 review, problems 3 and 4. So let's take a look at problem 3. What we're given is that sine of x is -2/7 and x is between pi and 3 pi over 2. And we're asked to find the cosine of 2x. So you might have a different value than -2/7. You might have a different quadrant than between pi and 3 pi over 2. But you're probably being asked to find cosine of 2x or sine of 2x. So here are the things that we want to point out. Here are the things that we want to note about what's going on here. So we're asked to find the cosine of 2x. So this says, we're going to be using a double angle identity. So right now we can see the problem is about a double angle identity because I want to know the cosine of 2x, and I have information that says sine of x. So I'm given sine of x, I'm going to want to write the cosine of 2x. But I also have this piece of information that says x is between pi and 3 pi over 2. What we're being told here is that x is sitting in the third quadrant. So this piece of information tells us that x is in quadrant 3. We want to think about what this means for figuring out cosine of 2x. If x is between pi and 3 pi over 2, that tells us that cosine of 2x, or sorry, just the 2x is going to be between 2 pi and 3 pi. So if x is between pi and 3 pi over 2, one thing that we'll notice is that if x is between 3 pi over 2 and pi, if I multiply everything by 2, then we'll find out that 2x is between 2 pi and 3 pi. So if x is in quadrant 3, 2x is going to be in quadrant 1 or quadrant 2. But the most important part is that we have the cosine of 2x, which says we're going to be using a double angle identity. Now we have multiple versions of the double angle identity for the cosine of 2x. So our double angle identity for the cosine of 2x, we could say that cosine squared x, you write it the other way around. No, we're just given a range of values that x could be. That tells us a range of values that 2x could be. So we're told that x is between 180 and 270, and that means that 2x must be between 360 and 540. That might not even be relevant to our concern. We might not be concerned about that. We just want to make that observation. When you see that expression, x is between pi and 3 pi over 2, you're given information about where x is located. It makes sense. X is in quadrant 3, sine of x is negative. So makes sense. All right. So let's think about our double angle identities for cosine. So cosine of 2x. Now there's a lot of ways that we might remember this. Remember the cosine is the cosine, cosine, sine, sine. That's because cosine of 2x is going to be cosine squared x minus sine squared x. Perhaps we remember the cosine of 2x as the cosine of x plus x, and the cosine is cosine, cosine, sine, sine. Hey Siri, what are the double angle identities? And then, of course, we've got our favorite way to remember our double angle identities. I have to scroll past some ads. There we go. Cosine of 2 theta is cosine squared minus sine squared. That's useful, but it involves cosine and sine. But we had multiple versions because of our Pythagorean identity relating sine squared and cosine squared. So cosine of 2 theta is, of course, when I get text messages. Cosine of 2 theta is 2 cosine squared minus 1, or more relevant to our interests, 1 minus 2 sine squared. I like that they have the cosine in terms of the tangent. That's good attention to detail. Because if you just look up double angle identities, and just grab the images, usually you don't get the tangent one. Usually this is what you end up looking at. But we got the 1 minus 2 sine squared, which is the one that's going to be relevant to our interests. But let's write all of them down because we're trying to remember stuff. So I want to use that third one because that's the information that I have. I have the sine of x. So the cosine of 2x will be 1 minus 2 times the sine of x squared. So negative 2/7 squared. Negative 2/7 squared is 4 over 49. And that'll be positive. And we can multiply by 2. So we got 49 49s minus 8 49s will give us 41 49s. We can also just treat 1 and 8 49ths as a mixed number and do 49 times 1 minus 8. Yes. Why is what's that? Because we're taking 1 and subtracting the 8 49ths. So it ends up being positive. So in this case, we can get a common denominator with 1 being 49 over 49. You can also just do the mixed number thing. So if we have something like 2 3/5, we multiply around. We take the 5, multiply by 2, and add the 3. How many people, has everybody learned that trick? To take 2 3/5 and turn it into an improper fraction, you do 5 times 2 plus 3. Has everybody seen this one before? You kind of go around this. You multiply here, and then you add here. So you do 5 times 2 plus 3, and then you just keep the denominator. So 2 times 5 is 10, and 3 is 13 over 5. This works because we're taking the 2 and we're adding the 3/5 and getting a common denominator. That 5 times 2 part, that's getting the common denominator. We're looking at the 2 3/5 as 2 and 3/5. And then we want to get a common denominator, and we do that by multiplying the 2 by 5 over 5. So this becomes 2 times 5 over 5 plus 3 over 5. Where you multiply the denominator by the whole number and then add the numerator, that's just a shortcut to getting the common denominator. It's no different. You're still getting a common denominator. There's the only difference between writing 2 3/5 and this 1 minus 8/49 is that we just assume that the 2 3/5 has a plus in between it. Even though when we read this fraction, we say 2 3/5. And it just means 2 plus 3/5. This is just 1 and negative 8/49. So we could do the same thing over here. 1 minus 8 over 49. 49 times 1 minus 8. No different. Same operation. It's just a shortcut to the same operation of getting a common denominator. Getting a common denominator is just understanding how addition works. We only add things that are the same, and when we add them, it doesn't change what they are. Sameness in terms of fractions is a common denominator. This works with polynomials as well, by the way. So if we have like 1 plus, let's go with 2 plus 3 over x minus 5. We wouldn't just write 2 and 3 over x minus 5. We write 2 plus 3 over x minus 5. It's only when we're taking a whole number and putting another fraction on it, proper fraction, that we don't write the plus in between. This is because apparently we have to have weird rules for shit, but we can do the same thing. We multiply here and then add, multiply and then add. This looks a little different because this is 2 times x minus 5 plus 3 over our denominator of x minus 5. So 2x minus 10 plus 3, 2x minus 7 over x minus 5. That's the same thing as if we get a common denominator between the 2 over 1 and the 3 over x minus 5. Here we are getting our common denominator because we're thinking of this as 2 over 1. And this leads us to the same place we just were. Any questions? Yes. The identity we used was a double angle identity. Double angle identity. So we were told that we figured out that 2x would be in quadrant 1 or quadrant 2. And since the cosine of 2x ended up being positive, it looks like 2x is in the first quadrant. So it looks like our 2x is in quadrant 1 because when we have found the cosine, it ended up being positive. This is not the only way we could have approached this problem. This was the intended way of us approaching this problem. So whoever wrote this problem intended for you to say, oh, I see this cosine of 2x means I should use the double angle identity. But we don't have to do that. We're told that sine of x is negative 2 over 7. And we're told that x is between pi and 3 pi over 2. You could use this information to figure out what x is. So our reference angle is going to be sine inverse of 2/7. Since x is between pi and 3 pi over 2, we must be in radian mode. So let's be in radians. And then just do a sine inverse of 2/7. I just want a reference angle, so I'm not worried about the negative part. So I'm going to put a reference angle of 0.2898. And we're going to put that in quadrant 3. So our x is going to be 0.2898 in quadrant 3. So I'm going to take pi plus 0.2898. So 3.4313. We could use this to figure out what 2x is. $6.8627. It's really annoying to take something that ends in 3, multiply it by 2, and have something that ends in 7. That's the origin of shit like 2 plus 2 is equal to 5 for very large values of 2. But I digress. Now we can just find, we want the cosine of 2x. So let's just find the cosine of this number. 0.836. So now we could just use the cosine of 2x. Cosine of 6.8627. It's been rounded off. That's okay. I kept all the digits on my calculator. 0.8367. I doubt that it still has all the digits. It still has enough digits to read that this is 41 over 49. multiple ways to get at the answer to the problem. Clearly, the intended way was to use a double angle identity because this is in the chapter in which the double angle identity resides. But if you know the sign of x is negative 2/7, and you know that x is in the third quadrant, you can figure out what x is, figure out what 2x is, and then just find the cosine of that. The best way to do it is whichever one of those methods occurs to you first. Also notice that we concluded that 2x was in quadrant 1 and 2x is in fact in quadrant 1. So note. Two x is in quadrant 1 as expected. Okay. Problem 4 is similar. We've got tangent of x is negative 3/7, and we want to find sine of 2x. Uh-huh. Where do you see practice test? Oh, so the first line is the source of the problem, the chapter. It's chapter 5 from the practice test. This is question 10. So notice that this is problem 4 on this assignment. Problem 4 is from chapter 5, the practice test in chapter 5. Every chapter has a practice test at the end of the chapter. No, this is just the source of the problem. Yeah. So if it said chapter 5.1, question 32, that's just if you open the book, chapter 5.1, look at question 32, that would be this problem. So if you open up the book to chapter 5 practice test at the end of the section, look at question 10. That's what I used for problem 4 on this assignment. Yes. Nope. It's from the book. Oh, yeah. I don't really spend a lot of time doing degrees minutes per second. We just decimal degrees. Calculator can do degrees, minutes, and seconds. So if we have like a 37.5 degrees, but I have to remember where it is. It can convert to minutes and seconds. Nah. Is it under angle? Angle. Convert to DMS. DMS is degrees, minutes, and seconds. So 37.5 degrees is 37 degrees, 30 minutes, and 0 seconds. 1 minute is 1/60th of a degree. And so if I had like a different angle, 37.58, if I convert that to degrees, minutes, and seconds, it's 37 degrees, 34 minutes, and 48 seconds. Okay, we got decimal degrees, and that gets us, but we don't have decimal time, right? So I wouldn't call the time right now. You say it's 140. I think I already see the clock. 144. So we'd say 144. We don't say 1 and 44/60 of an hour. But that's what the 44 is. The 44 is 44/60. So we don't get to be mad about degrees, minutes, and seconds. If we say what time it is right now is 1:45. Yes. No, that's just standard position measuring. It makes sense in context of where we start, and probably has to do something that's counterclockwise is evil or something like that. Everybody can read a clock. It's 1.75 o'clock right now. Yeah, I like when old people make fun of young people for not being able to read that clock. I'm like, oh, motherfucker, if you never taught the kid to read the clock, why would you think he should be able to read the clock? Oh, these kids today don't know how to change the oil. Oh, when did you teach the kids to change the oil? Well, I didn't. Do you think they're just fucking born with that information? Is this like genetically passed on? If you want them to know a thing, then, fucking teach them a thing. Yeah, because cursive is awful. No one can read in cursive. That was a weird skill that we used to have to acquire because all our grandparents write this fucked up script. It's ridiculous. Send me a text. Because look at all the spelling errors you can put into a text and still figure out what the message is. You know what I mean? Clearly superior. If you start misspelling things in cursive, all of a sudden it's really hard to put together what you're trying to say. It's bad communication. And when old people are like, oh, young people these days can't do this or that, because no one does that anymore. Send me a text, Grandma. I don't know how to do that. Oh, these old people, they don't know how to do shit that everybody knows how to fucking do. I just get mad when older people crap on younger people for not knowing how to do a thing that they never taught them to do in the first place. Oh, why can't these kids do math? Because we don't fucking teach them math. That's why. Do you know what I mean? I know. How are you going to get by if you don't know Morse code? I don't know. How do we get by for the thousands of years of human civilization before we had Morse code? Kids don't know the Morse code. Great, set up some telegraph lines. You know how to do that? Didn't think so. Didn't think so. I almost knew because I got two of my uncles were linemen for. It's way worse for keyboards because with keyboards we have to hold our hands in kind of an unnatural position. That's like the bad thing. Anyway, what are we talking about? Oh, yeah, kids these days. Kids these days don't know how to do stuff.
Why did they?
It was just because we had to write things so much, and it's faster. Because everything's connected. Instead of stopping and then writing the next letter and writing the next letter, it's faster and smoother. And we had a system in place where everybody could be programmed with the same script. That's why if you look at a lot of old letters, if you look at a lot of old handwritten stuff, the script is very similar. Because if you wrote it wrong, you got it wrong. You were programmed to write exactly the same. Does that make sense? We don't do that anymore for, I don't know, whatever reasons. It's not even computer to make this relevant. In fact, it probably has something to do with computers. But if you go, there are plenty of other educational systems. There are plenty of other educational systems where students are taught a very uniform way of writing. And if you look at handwriting samples from those of students from those systems, there's a lot less variability than you get from students in an American system. In an American system, students are like expressing themselves artistically through the letters that they write and the way that they write letters. But the reason you don't see that in the past is like, oh no, you write it this way. And there are still some systems when they're teaching writing, no, you write it this way. And it has to be written that way. And so there's a lot less variability in the writing style from person to person. We also used to, is anybody here left-handed? I don't know if we have enough people to have a left-handed person. You go back far enough, and this is not even that far. There are people alive today that this happened. If you wrote left-handed, that we had to put a stop to that. So if there's somebody in the class that wrote left-handed, that was naturally left-handed, that's how they wrote. As a teacher, I would have to put a stop to it. And depending on the school, like if I saw you writing left-handed, I would like hit you with a ruler, trying to get you to stop writing left-handed. I don't know. There's a reason that's sinister, and sin is like left. Because it's the devil writing backwards or some shit. Because people didn't understand something. Because I don't know, humans are idiots. But we used to try to program people to be not left-handed. You know what I mean? It's weird because the way we develop a system that's built for right-handed people. Because most of us are right-handed. And so if you're writing in ink, yeah, you'll end up smudging the ink. You're going to smudge the ink because of the way we designed our writing system from left to right. So if you're trying to go from left to right with your left hand, you have to hold your hand in such a way so that you don't smudge it. So it's like, oh no, don't do it that way, just conform. Just do it this way. Instead of adapt. You know what I mean? So that's kind of, it's very inconvenient. I've tried to figure out how to write left-handed once, because I was working as a tutor. And if I'm sitting in one position, I have the student sit on my left so that when I wrote something with my right hand, they could see it being written, right? So if I'm here and you're sitting here on my left, when I'm writing, I'm not covering it with my hand. But if you're over on this side, you can see me writing this down as it appears. But if you're on that side, if I start writing, I'm blocking what I'm writing with my hand, right? So I said, well, if I have a student over on my left, if I want a student on my right, then if I learn to write left-handed, I could write left-handed for that student and then write right-hand for this student, teach two students at once. Oh man, that's hard because you're like, oh, this is only going to be temporary, and I couldn't make it happen. I couldn't write left-handed. I got better at writing upside down. And I'm like, okay, second student just sits directly across from me, and I'll just write upside down for them. I don't know why I could do that right-handed, but not just left-handed. I don't get it. You know what I mean? What are we talking about? Right-handedness. So if you look at data, If you look at data, it looks like there are more left-handed people now than there were in the past. There aren't more left-handed people now. It's just that it's become acceptable to be left. We didn't just like try to feed it out. I mean, literally, I'm not kidding. Feed it out of you. Schools like saw you writing left-handed, they would beat you to stop you from doing it. And then we sit there and wonder why kids don't like school. No, they just ruin both hands and poison the student against school. Make the student hate the school. Good job. But back then it was only like, oh, it's only like a small percentage of the population is left-handed, because some of them are afraid to be left-handed. You know what I mean? So anyway. What are we talking about? That's why my script is so weird, because it's this weird combination of the cursive that was attempted to, it was attempted to be taught, and like just the regular print that I write slower in, which has become faster now. Because now when I try to think of how to make a cursive B, I'm like, oh, wait a second, what do we do? Oh, yeah. If I wrote it fast, then yeah. I start writing it, I'm like, I'm just going to text them. Yep. Yep. Yeah. One of my good friends' penmanship is so bad. I work under the assumption that he is left-handed. That if he just been taught to write left-handed from when he was a child, that I'd be able to read his writing. But even he can't read his writing. It's like a serious problem. It's a good thing that we can type most of our communication, because it's just bad. I've learned to decipher it through years of study, but I can say that on the internet because, first of all, no one's going to watch the video, and they're not going to figure out which one of my friends has the illegible handwriting. What are we talking about? Oh, yes. So we got the tangent of x is -3/7, and we're told that x is between pi/2 and pi. So if we think in degrees, there's degrees before. This is like between 90 degrees and 180 degrees. So this is information that's telling us that x is in quadrant 2. That makes sense. X is in quadrant 2. The tangent of x should be negative, and it is. So that tracks. In this case, we want the sine of 2x. This once again says double angle identities. We can also use the tangent of x equals -3/7 and figure out what the angle is, and figure out double the angle and take the sine of that angle, like we did in the previous problem. Or we could look for a double angle identity. Now, so we have the tangent, and our standard list of double angle identities doesn't involve, doesn't have sine of 2x based on tangent of x. I got sine of 2a. The only one available is 2 sine a cosine a. And we're given tangent. Tangent x equals we could also use so we have tangent. We could use that to figure out secant. Which one does secant get us, though? If we take the secant and flip it over, what does that give us? Secant, well, 1 over the secant is cosine. 1 over tangent is cotangent. So that's not related to sine. 1 over, but tangent maybe is related to secant. That's a good idea. But secant is related to cosine. But cosine is related to sine. So that would be could be a way to go. We could do sine and cosine for tangent. 1 over tangent is cotangent. So tangent squared is secant squared plus 1. Or wait, no, tangent squared is secant squared minus 1. Right? Oh, cotangent squared. Yeah, we could flip it over. So cotangent of x is negative 7/3. And cotangent squared, oops. So what's the Pythagorean identity involving cotangent? Do we know that one offhand? This is the one that I was thinking of. One's like this. Sine squared plus cosine squared is 1. So tangent squared plus 1 is secant squared. Cosecant squared minus 1. No, these are just Pythagorean identities. We're just trying to come up with ideas. Cotangent is cosecant squared minus 1. And cosecant is 1 over sine. So I could use this to figure out the sine of the angle. But I also need the cosine of the angle. Right, so because I had sine of 2x, the double angle identity for sine that we know is that sine of 2x equals 2 sine x times cosine x. So this we could use to get sine of x. Also, if tangent is negative 3/7, we could also use the tangent squared. X is secant squared x minus 1. And secant squared x can be used to find cosine. With some square root shenanigans, I can get those two. Once I have these two, sine x and cosine x, I can just drop them in my trig function, or my double angle identity for sine of 2x. That'll work. That's a plan. What do we think of this plan? Well, we need to know what sine and cosine are. Tangent is, we have tangent. That's what we're given. So we could get there doing identities. Cool. Let's take a break, come back with some other ideas. Middle of the class cliffhanger.